separate lectures here. One is really about Gödel surfaces, especially from graded rings. And the second lecture is about finite threefolds and birational rigidity. So there are also graded rings in there. But the two subjects are not really connected in any very close way. So you know, I mean, this is the last lecture of this series, and I don't want to sort of assume everybody knows everything that went before. And so I think everybody knows Gödel surfaces are surfaces with chi of OS equals 1, k squared equals 1. And let me just say k ample. You can, as usual, weaken that to nothing big. And so the classical way of constructing this is to take, so let me talk about the Z mod 5 Gödel. So the idea here, I mean, this is a very simple idea around, I don't know, in the 1930s anyway. So I take P3 and I take the group action that we now call 1/5 of 1, 2, 3, 4. So in other words, this P3 has coordinates x1, x2, x3, x4, and these are eigen coordinates for the group action Z mod 5. Right, so these are the non-trivial characters of the group Z mod 5. Or in characteristic 0, this is mu 5. After I make a choice of root of unity. Right, and then I take a quintic surface, Q5, in P3, which is invariant. Right, and since I chose these eigen coordinates, I chose the group action in this simple way. If I can do, for example, x1 to the 5th plus x2 to the 5th plus x3 to the 5th plus x4 to the 5th, and then I can put in plus other terms. So, for example, I can put in x1 cubed, x3, x4, plus other terms. So there's actually a 12-dimensional vector space here. Right, but let me just forget the rest, and this is just the simplest thing I can possibly do. So if I take this guy here in characteristic 0, then this is non-singular. And so the group action Z mod 5 on P3 has as its fixed points the eigen points, the points where so fix of Z5 is the PI. Non-singular, and so these xi to the 5th are non-zero at that point, and no fixed points. So I get S is the Q5 divided by the group action, Z mod 5. And so, you know, both of these characters, this is 1/12 of C1 squared, 1/12 of C1 squared plus C2, and this one's, so both of these characters just get, so this has chi equals 5 and k squared equals 5, and they just get divided by 5, and I get this S has these invariants. So actually, you know, except for one little trick in characteristic 5, this is going to have PG equals 0, Q equals 0. And so we find the Z mod 5 again as Z mod 5 included in the pick of S. Or it's also equal to the pi 1 of S. So, you know, there's sort of various exact sequences and so on in different kinds of cohomology you can write down to get this. Yes? And so, you know, this is really a nice example, and you can sort of learn a lot of things by playing with it. So, you know, I want to talk about two little things here and then go on to some of the other cases. So when I replace Z mod 5, when I replace Z mod 5 by Z mod 3 or Z mod 2, things get considerably trickier. So I want to talk a little bit about how you do the Z mod 3 case, and the idea is that I'd really like to be able to play the same games with the Z mod 3 case and the Z mod 2 case as I do with the Z mod 5. So, you know, games to play with Z mod 5. So one game is that I can extend Z mod 5 to the dihedral group D5. So, you know, nothing clever, there's nothing especially difficult about this. And I've got this group element A, which acts by a fifth of 1, 2, 3, 4, and then I can do B, which does x1 goes to x4, x2 goes to x3, and you can easily see that this is the dihedral group of order 10. Right? And if we just took this baby example, this first diagonal hypersurface, then it's obviously invariant under D5 as well. So, you know, this group has the diagonal elements A. Diagonal elements are A, Z mod 5, which is all the powers of A, and then B. And B has fixed locus x1 equals x4, x2 equals x3. So that's one component. And the other component is x1 plus x4 equals 0, and x2 plus x3 equals 0. Yes? So this is, so as far as P3 is concerned, here's P3, and the fixed locus is one line here, which I might want to call L plus, and one line here, which is L minus. Right? But if you think about how this meets this hypersurface, so Q5 here, let me choose this one to be L minus, right? Then if you look at the Q5, x1 to fifth plus x2 to fifth plus x3 to fifth plus x4 to the fifth, right, then obviously it intersects the L plus in 5 points transversely, right? These are the points, I mean, if I just take this set of equations, this is given by x1 to the fifth equals x2 to the fifth, or maybe minus, right? Intersect L plus. This is 5 distinct points, they're just cyclotomic roots, right? But on the other hand, the Q5 contains the L minus identically, right? Just because, you know, x1 to the fifth plus x4 to the fifth is identically divisible by x1 plus x4, and the same there. Right? So when you take if you take the quotients, you get a. So if I do this. Yes, okay. If I do Q5 divided by B, B is this is a reflection in here. This has branch line, which is non-singular, and then it has plus 5 singular points. Right? Or if I think about the whole Galois tower, so here is, I start off with Q5, and I can map down to the Godot surface X, and then this is Z mod 5, and then this is the quotient D5 modulo the central Z mod 5, sorry, the normal Z mod 5, this is Z mod 2. Right, and this is going down some surface F here. Right, and then, you know, all of these guys intermediate thing, Q5 over B. So remember, the dihedral group has, as I said, the diagonal group, and then all the other elements are A, I, B, are all reflections. Right, so if you think about what AIB is, it's sort of basically the same as this, but with little powers of epsilon here that I'm not bothering to write. Right? So if you think of all the 5 reflections here, then between them they have not one fixed line and 5 fixed points. They have 5 fixed lines. They have this line L minus, and it translates under A, and these 5 points, and their translates under A. So there are 25. So anyway, the upshot is that this action here has 5 isolated fixed points, and a curve which is so gamma with gamma squared equals -3 fixed line. Right? And so, I mean, everybody knows this. This is a very familiar story. So who is the surface F? The surface F is our conic bundle. So it looks like this. It's a conic bundle over P1, and it has 5 singular 5 line pair fibers. And these are the 5 nodes of the group action. Right? And then what happens to this curve gamma? Well, you know, it's sort of surprisingly complicated. This curve gamma is going to do this. It's going to have degree 6 over the base, but it's hitting each of those line pairs in 3 plus 3. Yeah? And so, you know, this is a... I have this little paper called Campodelli versus Godot. So here I had the D5 and the group action D5 on it. And everything I'm saying here is very, very simple and elementary, and you can calculate everything here completely explicitly, you know, basically just thinking about it. Whereas if I give you this question, so, you know, this is birational 2, this picture, P1 cross P1, with 5 special fibers here. I'm not going to draw 5 of them. And the branch locus has, so the branch locus in P1 cross P1 is 7, 6, and it has 5 times 2 triple points. Right? So this picture here, you know, so you can start from this if you want to. Imagine that I've got P1 cross P1, I've got a curve in it of by degree 7, 6, degree 6 over the base, degree 7 in the other direction, and this has these the singularities here. So I have R0. R0 is really just the image of gamma, and then R0 plus 5 fibers through the singularities. Right, and then I can take the square root of this, and then I can resolve singularities and take a minimal model and so on, get back to this. However, if you think about this picture, it's really jolly hard to imagine how you're going to find this. So if I fix the 5 fibres here, and I fix the 5 pairs of points on the 5 fibres, and I ask to get the curve R0, then R0 is superabundant. Right? So, I mean, this is the curve R. I should, let me call this R again. Right, ramification locus. I'm sorry. There's a curve L, which I'm calling L minus, contained in X. And this is mapping down to this curve I'm calling R in F. So in X, this was a curve L minus squared is minus 3. Look, everybody here knows this. So, and R squared is minus 6. Right. So the R0 is superabundant. So this curve has a normal bundle, H0 of O, has a normal bundle O F of O R of R, which is OP1 of minus 6. And this has H1 equals 4-dimensional, 5-dimensional. So if I fix these 10 points here and I ask, right, a curve of degree by degree 7/6 with these 10 points as triple points, then I will have a problem which is superabundant. It can only exist if some matrix has got rank drops by 5. And this is computationally a completely impossible problem. This is something that we have absolutely no idea how to do by explicit calculations from here. Right? So this is something that's given to us for free from here. On the other hand, we have absolutely no idea how to calculate it a priori from here. I mean, or even to prove that it exists without knowing this construction. So the singular guy R0 is basically impossible to predict or to calculate with. Right, whereas the original thing is really very easy. I'm just asking the dihedral group about the simplest group you can possibly have, and then acting on a hypersurface, which is more or less the simplest thing you could ask for. Yes? There's another question about this, is if I can construct this R0, and take the square root of R0 plus 5 Fi, right, and then resolve singularities, then what is pi 1 of the cover, of the resulting cover? So, what is it that that gives this picture fundamental group of order 5? So here I've got a rational surface. This is simply connected. I've got some curve line on it like that, which looks pretty harmless when I draw a picture. And then when I take the square root of it, suddenly I get this fundamental group of order 5 coming up. And where does it come from? Well, it comes from some funny linear system of curves here, which has 5-fold tangency points with all of these curves, and basically it's hopeless to calculate with. So there's a simple idea here, which is the quintic in P3 with a little group action on it, and there are these kind of things which in some ways are kind of more primitive, more elementary. Seem to be more elementary, but actually just impossible calculations. So, so this is one kind of little game you might try to play. So, I don't know whether there are pictures like this with exactly the same numerical specification, you know, the bi-degree like this, the number of singular points and so on, that have fundamental group of order different from this 10 here, this 5, where the double cover has, for example, 3 torsion or no torsion at all. So it's quite possible. Incidentally, so you know, you can actually see this map to P1. Right? This map, if you think about this variety in P3, I can do the L minus, the lines through L minus. It's just the linear system given by you know, x1, x2 or something. That's the projection to P1. So all of this is really extremely you know, precise and so there are interesting questions about trying to make the dihedral group of order 5 of order 10 in characteristic 5, which I think some of you know something about. But in any case, the hypersurface here is by, you know, far and away the simplest object you can possibly deal with here. The group representations in modular characteristics get a little bit messy. Okay, so this is one area of problems. Then I want to discuss another little point, which is part of Sohail Iqbal's thesis. Again, this is a game that I think several people in the audience have tried to play or are familiar with, and it's very interesting calculation. So so this is Iqbal, 2011. So he says I can make Q5 with this action of Z mod 5. And I can arrange that Q5 contains an orbit of 5 disjoint non-singular conics. Right? So this means I can find a conic in a curve here C, C in Q5 in P3. This is a plain non-singular conic. I can arrange this here, and then when group Z mod 5 acts, it takes the C to C1 up to C5. And these are, as I say, disjoint and non-singular. Right? And when you do that, so this is a conic in P3, which means that K of Q5, which is O of 1, times C is 2, plus 2. It's a curve of degree 2 in space. Right? And so C squared is minus 4. And then, so I can take this C, I can take the Q5, and I can contract the 5 CIs to points in some surface. Let me call it Q5 bar. Right? And now this is a surface with 5 times a quarter of 1, 1 singularities. Yes. So this still has PG equals 4. We haven't changed the PG. These are rational singularities, but we have changed the K squared. K squared is K of this Q5 bar squared is 10. And then he proves, Sohail proves that this Q5 bar deforms to some surface y. Right, and this is all of this is still equivariant with a group like this. Right, and so if I take the quotient of Q5, I get a Goodall surface. If I take the quotient of this, I get a singular guy with one, because these CIs form an orbit with a single 1/4 singularity, and then when I move sideways, I get a non-singular. So this is a Q-Gorenstein deformation. It's the simplest kind. It's just the cone over the Veronese. I take hyperplane section through the origin, and I move it to a hyperplane section not through the origin. Right? And so this is the y is Campodelli with Z mod 5 as its fundamental group. And so Campodellis with Z mod 5 were known before, but this is this is saying that the Goodall with Z mod 5 and the Campodelli with Z mod 5 live together in a family. So it's a, it's a beautiful result. The method of calculating, though, is sort of basically just computer algebra. So let me explain Sohail's idea for proving this. Well, for proving the first part. I regard this as not completely finished work. I mean, it's the example is proved to exist, but it will eventually be done in a more satisfying way. So Sohail says this. So we're in P3 with the action of Z mod 5. And what Sohail says is this. I'm going to take L1, L2, L3, L4, L5, and M1, M2, M3, M4, M5. These are two general orbits of planes. Right? So, I mean, we're in computer algebra, so we might as well give these names. So I'd take L1 to be, for example, x1 plus x2 plus x3 plus x4. And then L2 might be, epsilon x1 plus epsilon squared, x2 plus epsilon cubed, x3 plus epsilon to the fourth, x4. And then do the same with m. So for m, I'm going to write down ax1 plus bx2 plus cx3 plus dx4. I'm just going to write down, etc. Hope you can see I'm writing down 5 hyperplanes here. Right? And then M1 is AX1 plus BX2 plus CX3 plus DX4. So, when you do this in computer algebra, you just fix A, B, C, D to be random elements of a finite field. And then swing them round. M2 is epsilon AX1 plus etc. Right? So, this is... so then the clever thing he does is this. He says Q5 is equal to L2, L3, L5 times L1, L4 plus L1, M4 plus M1, M4. Right, plus cyclic permutations. Yes? So this means, for example, here I'm going to do this to L3, L4, L1 times L2, L5. Yeah? And so the point about doing the cyclic permutations and adding is that I get something which is manifestly invariant under Z mod 5. It's a sum of, fairly simple terms. Each of them is a product of these 3 planes and a conic. And then when I turn them round under the group action and sum them, I get something which is invariant. So Q5 is is Z mod 5 invariant. And if I set Li equals 0, I get a non-singular conic and 3 lines. Right. So let me see if I can. So there are three values here, 2, 3, and 5, right? And so if I set L5 equals 0, then of these 5 terms, 3 of them will already be divisible by L5. Right. So I set L5 equals 0, and this gives, if I got it right, L1, L3, L4 times L2, M5 plus M2, M5. Right, so all the terms divisible by L5 just disappear, so there's no L5 here, right? And then plus L2, L3, L4 times M3, M5. Yeah? And so, you know, this is divisible by something or other. This is L3, L4 times M5 times a non-singular conic, L1, L2 plus L1, M2 plus L2, M3. Right? And so, you know, this is those 3 lines. They're not any old 3 lines. These are part of the coordinate system, the Li coordinate, well, I don't know how you want to think of it. But anyway, I get these lines. So these lines will be common to 2 of the planes, and then here is a non-singular conic. So that's the. So you know, it's sort of surprising that such a simple consideration worked. I've absolutely no idea how Sohail thought about this. I mean, it's one of these kind of ingenious constructions where you have to sort of work at it for 3 months and. Then suddenly it works, right? And so anyway, that's the construction of Q5 with his 5 conics. Then he goes to this Q bar, and then to do this deformation, well, you know, you have to write an email to Youngnam to find out which cohomology group it is. And then you have to write a computer program to kill the cohomology group. So you know, it's at the end there's a kind of asking the computer to calculate, to prove that some deformation space is 0, and the computer runs for 2 days and then says it's 0. So, you know, we don't really understand what's happening, but it certainly proves that the example exists. And so, you know, I don't know whether, for example, you can make another orbit of these conics, whether you can make not just one orbit of disjoint conics here, but 10 different disjoint conics on the surface. That will be rather spectacular and deform it not to a Campidelli, but to an immortality surface, surface with k squared equals 3, and the same Z mod 5. Anyway, so there are lots of problems remaining with this. It's a simple-minded idea, but very pleasant. Okay, so I mentioned the surfaces with Z mod 4 last time. Let me go straight on to Z mod 3, and this is basically, you know, a little computational challenge. Can you do the same thing with same games with Z mod 3? Good. So the same games, I mean, you know, add onto it a dihedral group action. There's group Z3 is, of course, also contained in the dihedral group order 6, which is the symmetric group. Or can you force this surface to contain planes, to contain conics in the same, orbits of conics in the same way. And the problem is that, so let me make a little kind of digression here, general remarks about surfaces of general type. And graded rings. So I want to get to talk about PG equals 2, K squared equals 3, and a sort of fairly complicated construction. Right, and I want to show that this complicated construction can be understood in a sort of civilized way, understood as something like a hypersurface, but you have to be clever to do it. Right, but anyway, let me just start with much more simple things. So everybody knows if I do PG equals 4, K squared equals 6, and I ask for the simplest possible construction of any surface like this, so then I'll get, you know, there's the canonical map, Ks. I'm thinking here Ks is ample. S is non-singular projective and Ks is ample. So this is mapping S to some surface S bar in P3. And, you know, one thing you can say is that this is I'm assuming this is a morphism. I'm assuming everything is as nice as possible. So one thing is clear, that this cannot be an isomorphism, right? Because the S bar is a surface of degree 6. If this were an isomorphism, then the S would also be non-singular. If it's a non-singular hypersurface of degree 6, then he has canonical class, not O of 1, but O of 2. And so we'd have PG, all the wrong number, K squared, all the wrong number, and so on. And so some singularity has to happen. And the thing that happens here is that there's a plane, x1 equals 0, and inside the plane I've got a cubic curve, f3 equals 0, and the image surface is double. Image S bar is double along this curve C3. Yeah, and so the canonical map sort of tries to put the surface into 3 space, and there's a kind of double locus that happens. The double locus happens along a plane cubic. So the best way to think about this is not geometrically, but not in the first instance geometrically, but algebraically. So we look at this ring, R of S and Ks, and so in degree 1, there is x1 up to x4, and then in degree 2, well, I ask Riemann Roch what is h naught of 2k, and the answer comes back is chi of OS plus k squared. Right? So this is 11. Yeah? And so here I'm going to write down, so I have these monomials of degree x, I have these generators x1 up to x4, so in degree 2 I certainly have the symmetric squares, the symmetric powers of the monomials, so I can write down that. So there are 10 quadratic monomials in x1 up to x4. I'm just saying this is the Newton polygon, x1 squared all the way to x4 squared. And so there has to be another element, y. Right? And we're taking this easy attitude that we're looking for the easiest possible case. So we think of these 10 as being linearly independent, and this y as being one new, one complementary generator. And then we study in degree 3 and degree 4, and we find one relation. And I can call this relation x1 times y equals f3. Right. So if I follow the monomials, these monomials up into the next degree, I've got cubic monomials in the xi. You can calculate easily how many there are. And then I've got the xi times y. You can also calculate what is h naught of 3k. and you'll find there must be one relation like this. So this is saying, well, y is not in the ring generated by x1 up to x4. However, if I allow myself to take quotients of the xi, I can write this y as f3 over x1. And, you know, so the map is birational. The map is birational, and, you know, the y here is appearing as the thing that separates the double locus. Right? And then one relation here, and that's y squared equals g4. Right? And then we'll find that S bar is eliminate y to get the equation. So the equation is x1 squared g4 equals f3 squared. Yeah. If you think of the x and the f here as being the x and the f and the g as being fairly general, and this is just the thing I've just written down is the general solution to writing down a hypersurface of degree 6 in P3, which is double along this curve. Yes. So, of course, this construction is due to Enriquez, and Enriquez would have been the first to point out, oh yes, there's lots of different accidents that can happen here. So Horikawa studied this in great detail, and then what was their names? Bauer and Catanese. Bauer, Catanese and Pignatelli. You know, this is, in some ways, this is sort of, I mean, this uses graded rings in the complicated cases. And it's quite a complicated story. So, so let me just skip this. So, you know, different degenerations can happen here. And I think it's still an open problem to know whether the surfaces in the different components of the moduli space are diffeomorphic or can be moved in algebraic families into each other. So this is a kind of, you know, this is the first, and so if I take the variety defined by these equations, then what he is S embedded in P of 1, 1, 1, 1, 2, and his S is you know, F3 intersect G4. Right? So this is a kind of model case in which using rings it gives you the construction of a variety. Right? So I want to see, can we do the same with these invariants? And then I want to have Z mod 3 invariant, Z mod 3 action. And so, you know, I mean, I solved this problem in my first paper in algebraic surfaces in 1977. And then about 25 years later, I discovered a much neater way of doing it. But let me just. So if I do this, PG equals 3, K squared equals 2, sorry, I got it exactly the wrong way around. PG equals 2, K squared equals 3 gives a codimension 4 ring. Or gives, you know, any candidate construction for this will give a codimension 4 ring. So these surfaces are constructed by a codimension 4 ring, and I'm going to show you that this is a Thom and projection. And so, basically, at the end of this, I'm going to say you write down a rather simple toric variety, written down by some sort of rather obvious equations, and then inside there I write down a couple of hyperplane sections. And then you get the variety. So this is just a little bit nastier than a hypersurface in P3 with a Z mod 5 action, but it's not that much nastier. And all the constructions I was doing here, at least you can hope to do play similar games with this. So let me say how this calculation starts. So let me write down straight away P of t. So this is, I'm trying to construct a surface S. So I'm going to write PS of t. This is the Hilbert series of RSKS. And so I think everybody knows this is 1 plus PG minus 3t plus k squared minus 2PG plus 4 g squared plus PG minus 3 t cubed plus t to the fourth divided by 1 minus t cubed. Yes? So this is just Riemann-Roch. So 1 plus PG plus, 1 plus PGT plus K, 1 plus PG plus K squared, T squared plus 1 plus. Right, so if you just think about this, then this power series is identically this power series. So in this case, this is, if I get it right, 1 PG is 2, this is minus T, and then 3, is this plus 3T squared? Let me try and impose a sanity check on this. If I sum these terms, if I set t equals 1 and sum the terms on the top there, right? I've got k squared, then I've got minus 2pg plus 2pg, and then I've got minus 6 plus 6, so I get k squared. So the sum of the terms on the top, the sum of the coefficients on the top has to be k squared. So what have I got here? I think I'm out by a little bit, aren't I? K squared is 3 minus 4 plus 4, this is 5. Yeah, and so when I sum this is 1 plus 5, 7 minus 2 is, and maybe it was right first time. Sorry, this is 3. Okay, so when I put so I'm going to write this as this is 1 plus 2t squared plus t to the 2t cubed plus t to the 5th. Yes. Sorry about that kind of mumbo jumbo, but this is a simple method of calculating. So this says what this is saying is that if I want to generate this ring R of S KS, I need generators x1, x2 in degree 1, and then y something. Let me hold fire as to what I'm going to call him in degree 2, right? And that's this denominator. Right, and then I can think about and then if I'm lucky, these three elements here will generate a subring, and the whole ring will be finite over it. And so then I need y, another two y's, two more y's in degree 3, in degree 2, and 2 times the z's in degree 3. Yeah? And so think of these guys here as being ring generators, and these guys as being module generators. Then I need two yi's here and two zi's here. And then this guy here, well, I do need to have as a module generator, but as a ring generator, it will just be a product of those two. Right. Anyway, there's a little calculation here which you can do very easily. So in my 1977, I think it was, Tokyo paper, I say this ring needs generators. So x1, x2, and then y0, y1, y2, and z1, z2. And I can take these to be eigen functions for z mod 3 action. Okay, so if you do this, you're going to find, so this is saying that the right place to look to try to construct this surface is contained in P of 1, 1, 2, 2, 2, 3, 3. So 1, 2, 3, 4, 5, 6, 7. This is P6, so this is codimension 4. Right. So in that, in this Tokyo paper, I say we need. So I mean, this same Hilbert series, PT, is also equal to. Divided by, so I'm sorry, I'm going to write 1 minus t squared, 1 minus t squared cubed, 1 minus t squared squared, t cubed squared. Right, so these are for these generators. I put in each of these polynomial generators times p of t. This is equal to 1 minus 3t to the 4th minus 3t to the 5th minus 3t to the 6th, plus 2t to the 6th, plus 6t to the 7th, plus 6t to the 8th, plus 2t to the 9th, and then symmetric. Okay, so this is saying, if I want to generate this ring, the simplest thing it can possibly be is these generators in these degrees, and then 3 relations in degree 4, 3 in degree 5, 3 in degree 6, and then syzygies coming along here. So this is a 9 by 16 resolution. Okay, so I must have these 3 equations here in degree 6 and 2 syzygies in degree 6. That's just to handle z1 squared, z1, z2, z2 squared. I want z1 squared, z1, z2, and z2 squared to be finite over the ring. So I want there must be 3 relations of degree 6 there. And then you in this, I'm going to give you the modern treatment of it, but the modern treatment starts these 3 relations, and these 3 relations can be written as things like so 3 relations in degree 4. So they look like R0, which is x2 z1 plus x1 z2 equals y1 y2 minus y0 squared plus other stuff. R1 is x2 z2 equals y0 y1 minus y2 squared plus other stuff, and so on. Three relations in degree 5. So, in other words, these are using, because of the group, because of the Z mod 3 action, these are not any old monomials. So I'm writing down really quite special monomials. And then you can think about taking cyclotomic combinations of these. Have a nice factorization. So actually this is I'm talking about, there's a little remark here which is just completely baby group theory. Completely. So if I have a representation, if I have a vector space with the action of one of these cyclic groups, in this case it's just the group of order 3, you can break it up into eigenspaces. So I was choosing these guys to be eigen coordinates, or you could also think of it as cyclic permutation coordinates. And so, that was also implicit in argument of Sohail that I've just rubbed off the blackboard. So I'm going to leave this just for a moment, forget about this just for a moment, and write down another ring. Write down the ring I want. And the ring I want is, as with, when you have a Thom unprojection, codimension 4 ring, which can be written as a Thom unprojection, it is related in some way to P2 cross P2. So here's P2 cross P2. Right. So what are the equations of P2 cross P2? Well, I'm going to take a 3 by 3 general matrix, and then I'm going to take wedge 2 equals 0. Okay? And I'm going to write down this matrix in a funny form. Right? I'm going to write them down like this. X0 X1 X2, and then Y2 Z2 Y0 Y1 Z2 Z0 Z1 sorry Z1 Z0. Okay, so you'll notice that here I have equations x I times zi is yj yk, and yi times zi equals xj xk, and zj zk equals xi yi. Now, at the moment, all these generators are homogeneous of degree 1, but very soon I'm going to twist that a little bit. Right? So I've written this down here so that I'm seeing the equations this x here is in the same row as that z and is in the same column as that z. So the only guy who multiplies is the x, is the z naught. Right? So there are 9 equations there, and I've written them in this sort of basically crazy way. Right? And now I'm going to change the equations. I'm going to write S there. Change the equations. This is like a deformation by introducing S. Yeah? So this is just completely harmless. I've introduced, if I set S equals 1, I just get back to the original P2 cross P2. And then I'm going to say weight xi equals 1, weight yi equals 2, weight zi equals 3, and weight s equals 3. Right, so if I do this, then this is weight 4, this is weight 4, this is weight 5, this is weight 5, 6, 6. So these are now homogeneous. So, you know, if you think about this, these are the equations of P2 cross P2, then you can make, I think, it's a representation of GL3 cross GL3, so there's a 6-dimensional algebraic torus that acts on it. I'm just choosing one particular thing. Okay, so this is a set of equations. I want to understand how to deform them, and I'm not interested in deformations of them that just leave them exactly as they are. And so what I'm going to do is this. I'm going to do Z naught hat. So project from Z naught. So the point is, you think about these equations, then Z naught hits X naught and Y naught and Z1 and Z2 and not anyone else. Right? So there are 4 equations here. There's a linear in Z naught, and then there are 5 equations without Z naught, without Z naught. Yes? So these 5 equations without Z naught, these are guaranteed to be Gorenstein codimension 3. And so this is, these are Pfaffians of x1, x2, y1, minus y2, y0, z2, 0, 0, z1, s, x0. Yeah, so you can see x2, z2 is y0, y1. That's one of my equations. x2, z2 is y0, y1. Yeah, and so, you know, this is sort of typical thing. You know, if I didn't have the s there, this is just the projection of P2 cross P2 from a single point. This gives me this Pfaffian matrix with two special entries here, right? So I say that this is Tom 1. Right? I want the x0, I want the guy z0 here to hit x0, z1, z2, and y0. So z0 hits the codimension 4 complete intersection ideal. x0, y0, z1, z2. Right, and the guys along the top are just arbitrary. In fact, they're independent variables. Yeah, so this is a model Tom unprojection. Yes, and so now I can vary this. So vary. This is deform. Vary the entries of the bottom 4x4 block in the same ideal. Right? And so then I get x1, x2, y1 minus y2, y2, z2. And then here I'm going to write down r1 x0. And here I'm going to write down r2 x0, z1. And then s x0 minus r0, y0. Right, so this is still, so I can unproject. right? And so, you know, I mean, so I'm going to be left with these equations, which look like this: x2 times z2. If you think about, if you think about this Pfaffian, this is x2 times z2 is y1, y2, and then this times this x1. I'm sorry, I've shuffled up the equations, but nevertheless. Okay, so. So what's my conclusion? So if I go to space, affine space with coordinates x0, x1, x2, y0, y1, y2, z0, z1, z2. S in degree 3, and I think R1 and R2. What degree are R1 and R2? R1, R2. So all of these are degree 1, all of these are degree 2, these are degree 3. Right? And then I write down the unprojection equations. So that's the 5 Pfaffians of the thing I wrote over there, the matrix over there, and 4 equations saying x times z0. So this z0 is the unprojection variable, so he's going to multiply x0, y0, z0, z1, and z2. Right? And you can figure out what has to go on the right-hand side of this equation. This is y1, y2 plus r0, x1, x2. And this is s, x1, x2 minus r2, x1, y2 minus r1, x2, y1. And this is x, x2, y2 plus r0, r1. And so on. I mean, it's this is mechanical. There's no choices involved here. This is just the Christian-Miller unprojection algorithm. Yes. And so these define codimension 4 Gorenstein subvariety of this A. Right, so 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, A12. Right, so it's a 9-dimensional key variety. Right, and then these equations, the equations I have here, I mean, I'm sorry, I've passed through a different basis. There's a cyclotomic change of coordinates here, but so I can think of this, if I want to, as in weighted projective space, you know, 1 cubed, 2 to the 5th, 3 to the 4th. This is with the xi, this is with the yi and the ri, this is the zi and the s. Right, so this is v. So this is some dimension, which must be 11 by now. This is codimension 4, so this one's 7. So my s, I can write s is v intersect 5 hyperplanes, 5 hypersurfaces. And the hypersurfaces are just setting Ri equals S equals and then x naught plus x1 plus x2 equals 0. Z naught plus z1 plus z2 equals 0. Right, so I write this is a function of xi and yi, and I write this is a function of xi, yi, zi. Yeah? And so the thing you notice is that there's a z mod 3 acts here by cyclic permutation. Right. And so, you know, this V is, you know, it's a perfectly nice key variety. And what I'm doing is I'm taking a key variety, and inside that key variety, I'm now taking hypersurface section. So, you know, this, if I didn't impose this, I would get not a surface of general type, but a Calabi-Yau threefold. If I didn't impose this, I'd get a Fano variety, and I'd also have some little 1/3 singularities there. Right? So this last equation here is avoiding the center of the projection that I used to construct the variety. Right? And so all these 9 equations, you know, are rewritten as complete intersection in a key variety. Right. And so, you know, if you want to know, can you, for example, add a dihedral group action to the cyclic group action, or can you do the same thing in characteristic 3, or can you do Sohail's unprojection trick, adding a conic to it and taking you from a Gödel with Z mod 3 to a Campodelli with Z mod 3, you know, this is the right way to start, the right place to start. So I haven't, of course, made any progress on this. This is a problem for the current generation. Okay. I should say this is in my this is in a paper. This is in a paper I called Kinosaki. So this is in graded rings and birational geometry on my website.